going. And, uh, yeah. Uh, Please feel free to interrupt me at any moment. I'm yeah. I I hope I will be able to reach to you, even though some notions will not be familiar. Um, and I tried to make it visual so as to be accessible. So the starting point is the following fact. So you consider a polytope P. So a polytope for me, this is the convex hull of a finite set of points in Rn. And you look at this map, the diagonal map, which sends a point to uh, the same point two times. And so, for instance, if you look at the simplest non-trivial polytope, it's the interval. And what's happening with the interval? Well, you take this. You take it and you send it in this red line here on the right. It goes right in the middle of the square, and this map, it is not cellular in the sense that the image is not a union of cell of the target, and so one is led to the problem of finding a cellular approximation that is finding uh, yeah, finding a cell. This is finding a cellular map which is homotopic to the set-theoretic diagonal in red, uh, but which is cellular. So for which like so the image is a union of cells, and so you have one of the possible two options here in blue. So you have to imagine that you deform this diagonal to the boundary as to get a cellular map. Uh, there's a there's a symmetric option. You could also deform it the other way around and to go through this other path on the unit square. Um, so actually, this is quite important in algebraic topology, since the famous I guess you've heard about the Alexander-Whitney map, which is basically nothing more than a cellular approximation of the diagonal of the simplices, and it allows one to define the cup product in cohomology, which is a very basic and fundamental uh, uh, algebraic data associated to a space. When you do this on cubes, well, when Jean-Pierre Serre wanted to study fibered spaces, he needed cubical cohomology, and he needed a cellular approximation of the cubes, and this was not really necessarily hard to define. But we'll see that for more complex polytopes, well, this can be more complicated. Okay, so let me talk very briefly about loop spaces. So if you have X topological space, and you look at you choose a base point, and then you look at all the loops in let's say you have your space X here, you have a point X0, and then you look at the set of all loops, that is paths that start and end at this point X0, and you endow them with a concatenation product. So this means that well, if you have a loop like the one in blue and the second loop in yellow, then you can make a loop out of them by just going around them twice faster. So you go faster, like you go two times the speed on the blue and two times the speed on the yellow, and then you get a new loop which starts and ends at x0. And the thing with this concatenation product is that it is not strictly associative because of this precisely because of this parametrization. So in notation, you have like strictly this F concatenation with G concatenation with H. It's not the same as F concatenation with G concatenation with H. And so you can see, but these two parameterization, one is on the top line here, And yeah, maybe I should use different colors. One is on the top line here, and there's another one on the bottom line here, and you can actually find an homotopy between these two parameterizations. And actually, so if you have these two parenthesization here, they're not equal, but they are homotopic. And if you take two homotopies between these parenthesization, well, it turns out that they are also homotopic. And so on. So all homotopies, there's a big tower of homotopies encoding this defect of associativity in loop spaces. And a DG model for these spaces is what we call an A-infinity algebra. So an A-infinity algebra, well, it's a chain complex together with maps mu n from A tensor n to A, which satisfy these relations. And it's not very, it might look a bit scary at first, but actually it's not very complicated. So you have to think about of this mu n as operations with n entries, like n copies of A, and one output, like that give back one element of A. And they satisfy the relations, well, it's basically summing over the ways, all the possible ways of splitting your tree into two. So, well, maybe I should put an additional leaf. So 1, 2, 3, and then you'll get 4, 5. And I will put one here on the right. And so the P, Q, and R that you're seeing in the equations, these are just the number of leaves here, P, Q, and R. And you're summing over all the possible ways of composing two planar trees to get one with a fixed number of leaves. Is this clear? Does it make sense? Yeah, I guess the picture is better than otherwise. So if you look at these relations, well, the first one is saying that actually the first one says that mu3 is a chain homotopy between the two ways of parenthesizing mu2. So it's really saying that associativity here, so this is, well, this is the picture, and this mu3, this corolla here. So the boundary of this corolla, which is to be thought of as an homotopy between the left and the right comb, say that the associativity it holds only up to one homotopy, and then the higher mu n's, they are encoding higher homotopies between homotopies. It's exactly the same picture as we had for loop spaces. And of course, when you declare all mu n's to be 0 for n greater than or equal to 3, then you just recover the ordinary notion of an associative algebra. So the problem that I'm interested in is the, well, let's say a starting example is this question here. So if you're given two A-infinity algebras, A and B, with operations mu n and nu n, then how do you can you endo the tensor product A tensor B with a non-trivial A-infinity algebra structure? So this means wait. So this means taking these. So you have the family of mu n's that verify these relations, the family of mu n that verify these relations as well, and then you want to find a family of, let's say, row n's that go from A tensor B tensor N to A tensor B, and which satisfy this relation here. But you can only use the fact that mu n and nu n do. So you'll get something like, so for row 1, this is going to be, this is not so complicated. It's just the usual differential. Yeah. Row 1 will be, yeah, sorry, I defined it only for n greater than or equal to 2, but you can also think of mu1 as a differential. But yeah, so yeah, row 1 would be the usual differential, and row 2 would be, it's just mu2 times nu2, and this is just the product, right? If you had two associative algebras, and then you want to make the tensor product of them, then you would just make the tensor product of the products, and then you get the associative algebra. But then what do you put as row 3? Maybe you'll say, oh, just put mu3 and mu3, but actually this doesn't work. Why? Because, yeah, already you can see it in terms of degree, because here, yeah, sorry, I didn't say that. All the mu n have degree n minus 2. And so if you look here, well, you should have row 3 of degree 1, but then mu3 and nu3 are both of degree 1. So this tensor product is of degree 2. So this doesn't work. So you have to find something else. And it turns out that this problem is really, it's really non-trivial. So the first ones to solve it were Sennenblitz and Humble in 2004, and they have some combinatorics that I don't know where their intuition come from. It's quite impressive, and it has really wonderful applications in the study of fiber spaces, for instance, in string field theories and mathematical physics, and as well in Fukaya categories in symplectic topology. Would be happy to talk more about some of these applications at the end if some of you are interested. But let's take another route to solve this problem, which is to take a more, to my opinion, it's a more conceptual point of view. It's the operatic point of view. So let me start by telling you a little bit what is actually an operad. So what is an operad? Well, it's a family of vector spaces indexed by the natural numbers, which you should think of as spaces of operations. So Pn, that's a family of operations of arity n, that is operations with, so if you have some mu operation in Pn, you should picture it in your mind as a tree with n leaves, and where this vertex is decorated by mu. That is an operation with n inputs and 1 output. So you have this in every arity. You have families, well, vector spaces of operations, together with partial composition maps, which are nothing more than, like, you can picture them by grafting trees. So if you have, like here, let's say a mu with 4, maybe let's say that mu is in P4 here. And if you have a certain, you are the circle I product, let's say a circle 2 with a nu that is with 3 inputs. This is, so it would be in P3. Then you have a way to compose them. So you put, basically it's just, you put on the second leaf of mu, you put nu, like this, and you get a new operation which has 4 plus 3 minus 1 inputs. So it would have 1, 2, 3, 4, 5, 6 inputs and 1 output. So this is, so an operad is basically a family of operations of all arities, and you have a way to compose them, and they satisfy the parallel and sequential axioms, which are just the tree-like generalization of associativity. So if they say basically that if you have you compose three operations like this, like these. So if you compose them, well, you have different choices, right? You can compose these two operations first and then compose with the third, or you can compose sorry, the two on the right and then compose with the one on the left. So you would get something like this. And then what is the first parallel? Here's the parallel axiom. It says that these two are actually equal. The parallel axiom says that these two are equal. And the sequential axiom is analogous. It's when you compose trees on top of each other. So it would say that the two ways of parenthesizing this tree are the same, basically. So you would get something like this and this. So these are, and this is the sequential axiom. So this is basically an operad. So the canonical example or the mother of operads is the endomorphism operad. So you look at the vector spaces of linear functions from V tensor n to V. And you can verify quite easily that these satisfy the axioms that I just wrote down. And so the three canonical three other examples of operads are the associative, commutative, and Lie operads, so the idea of an operad is that it encodes a type of algebraic structure. So well, here you have the definition of an algebra over an operad. You can always take an algebra over an operad, and it's basically a morphism of operads from your operad P to the endomorphism of V for a certain vector space V. This is really like doing multilinear representation theory, right? Because if you add only the from V to V on the right, then this would be representation, right? But here we're doing it for all arrays. And turns out that, well, when you take algebras over the associative operad, you get associative algebras. And the same with commutative and Lie operads. And they are related by causal duality. It's a beautiful theory. We would be very happy to say a bit more about it afterwards. Maybe just a word to say that operads, well, they exist in any symmetric monoidal category. So they actually come from topology. So they were designed in spaces. And there's this famous operad, which is the operad of the little disks. It's basically, you consider configurations of disks in the unit disk, and you compose them by inserting a configuration into one disk of another. So here, you're doing the circle one operation, and you're taking this configuration on the right, and you basically substitute it in the first disk on the left, and you get this new configuration of disk on the right, and this is the operatic composition. So maybe you've already thought about it, but there's we spoke about infinity algebras. These were the generalization of associative algebras to a non-strictly associative product. And it turns out that there's an operad, A infinity, which encode, when you take the algebras over A infinity, then you get A infinity algebras. And the very beautiful thing about this operad is that there's an isomorphism between the arity n component of this operad and the cellular chains on a polytope, which is called the associahedra. Maybe you've already heard about it. It was designed first by Stashev, the 60s, and it has been widely studied since then. And so the associahedron, what is this polytope? Well, it's a polytope whose, so the n-2 dimensional associahedron has its faces in bijection with planar trees with n leaves. So if you take the one-dimensional associahedron on the left, well, this is just it's just the interval, and you have this left come on the right, on the left, the right come on the right, and you have the corolla, which is in this is the edge in the middle. And here for the two-dimensional associahedra, you have four. It's all trees with four leaves. Vertices are binary trees, planar binary trees, and to get from a vertex to an edge, you basically contract an edge in the tree. So for this one, this edge, you would actually get this tree, because you contract the edge here, and the edge here. And if you want to get the edge of the polytope on the opposite side, you would get sorry. So you would get this tree, because then you would contract the other edge, and here this would correspond to contracting this edge. And of course, you have the corolla indexing the two-dimensional cell. So just take water. Is this picture clear? Is it? Do you see what I mean here? Okay, I guess it's the case. Don't hesitate to actually interrupt me. And then, well, in the three-dimensional associahedra, you will get something a bit more complicated. And the top cell, well, it's the corolla with 5 leaves, and then you'll get here as vertices, it's planar binary trees with 5 leaves. Yeah, absolutely. And then to go from a vertex to an edge, you would just contract an edge in the tree, and so on. So this is a DG. We're on the level of chain complexes, and actually you could wonder, well, but this operad structure, does it come from something at a topological level? Does it come from a topological operad structure? And it turns out that endowing the associahedra with a topological operad structure, it's really a non-trivial task. And now let's go back to our problem. So the initial problem with the approximation of the diagonal of polytopes. Suppose here that we have a cellular approximation of the diagonals of the whole family of associahedra. And suppose furthermore that we have a compatible topological operad structure on them. And hereby compatible, I mean that these morphisms delta, let's call them delta n. What I mean by compatible, I mean that delta n's are gathered together to form a morphism of operad. Form a morphism of operads between the operad structure on the associahedra and the operad structure on the Cartesian product of associahedra. Morphism of operads. Well, and then if you're able to solve these problems, you have actually solved the problem of endowing the tensor product of two infinity algebras with an infinity structure. And actually, the proof of this lemma is quite easy. It's quite straightforward from the theory. You have it here. So in two words, it's you take so if you have an infinity algebra structure on A and an infinity algebra structure on B, these are equivalently described as operad morphisms from A infinity to the endomorphism operads. Using the cellular chains functor on delta, you get a morphism of DG operads from A infinity to A infinity tensor A infinity. So this is just given by the cellular chains on delta. And then when you compose these morphisms, sorry, you obtain the operad structure on A tensor B that you wanted. So this lemma is very easy, but these 2 points here, they're really non-trivial. These 2 points are really non-trivial. But you see, we've translated the problem on the level of chain complexes. We've took it down to a problem about geometry, about associahedra and finding a cellular approximations of actual polytopes in Rn, and finding a operad structure there. So it has become well. Then you see where the tensor product comes from. And since this is what was done by Naoki Masuda, Andrew Tonks, Hugh Thomas, and Bruno Vallette, their article has just been published in the Journal de l'École Polytechnique. And what they do, well, they do exactly what I've been telling you about. So they define cellular approximations of the diagonal of the associahedra. Well, of course, they have to pick up a certain realization of the associahedra, because you can have many polytopes whose combinatorics are equivalent to the ones of planar trees. And they endow these realizations, the Lode realizations. They were designed by Jean-Louis Lode. These are very elegant realizations of the associahedra, and they endow them with a compatible operad structure. And they prove, finally, a formula for the image of this diagonal approximation. And this is equivalent to proving, to find this finding explicitly the formula for the tensor product of two infinity algebras. And they recover the formula that was found by Senneblese and Humble, which I mentioned a few minutes ago, and which was expressed a bit differently in Markel and Schneider paper in 2006. And what is this? So yeah, maybe a word about the method that they use. Well, they borrow ideas from the theory of fiber polytopes of Biera and Sturmfels, which is a very beautiful theory. I would be very happy to tell you a bit more about it at the end if you're interested. Another salient feature is that once you fix a diagonal approximation of the diagonal approximation, then you have a unique operad structure that is compatible with it, and this operad structure is really fractal in nature. It would be, I think, quite interesting to have someone in dynamical systems looking at it, and then and they solve this problem by using tools from discrete geometry. Now let me say a word about this magical formula. Why do we call magical formula? This is from the word. This is a word from Jean-Louis Lode. So we just need a definition in order to state it. So we will say that a polytope P is oriented by a vector V if V is not perpendicular to any edge of P. So let's take our two-dimensional associahedra, and let's pick up a vector that is not perpendicular to any edge, and then P is oriented by V. We can say that P is oriented by V. And as soon as P is oriented by V, you actually get a minimal vertex but P for the minimal in the sense that the scalar product with V is minimized. And you also always get a maximal vertex, and you get an orientation on the one skeleton of your polytope. So this is oriented polytope. And notice that since a polytope, if a polytope is oriented by V, then any face of P, which is also a polytope, is also oriented by V. Yeah, and in the face, well, like intuitively here, faces, you have 5 faces of dimension 0. These are the vertices. You have faces of dimension 1. These are edges. And you have 1 face of dimension 2 in the middle. And well, now the magical formula for the associahedra is the following. So it says that the image of the approximation of the diagonal, this is the union over the pair of faces F and G, which satisfy the following. They have top of F less than or equal to bottom of G. So here, if we translate, yeah, let's take this orientation vector for the associahedra, and then let's say that this will be F and this will be G. And then if you look at, so according to this orientation vector, you'll have here top F, and here you'll have bot G. And since they are comparable under this order on the one skeleton, FG is in the diagonal. Remember that the diagonal, it's just a morphism from P to P times P. So the faces of P times P, these are just pairs of faces of P. And well, if I took this edge as, let's say, G prime, well, since bottom of G prime here, it is not comparable to top F under the order on the edges. It is not in the diagonal. So you would have F G in the image of delta n, but F G prime, this is not in the image of delta n. And what the theorem says is, well, that's all. That's all that you need to know. And maybe I should explain what are these drawings in the middle of the associahedra on the left. Well, these are a subdivision associated to these pair of faces. So for instance, these 2 faces that I've put it in blue, well, they correspond to this part of the subdivision. And it's a pair in the image of the diagonal. And every time you take, like when you take all the pairs, you get all of these cells in the decomposition. It's quite elegant, isn't it? So this is the work of Masuda, Tonks, Thomas, Vallette. And so now we come to my work, which was the following. So we've talked about associative algebras, and we said that they were encoded by the associative operad. We also said that there was some A infinity algebras, so algebras associative up to homotopy, which were encoded by an operad A infinity. And it turns out that this A infinity is a resolution, the minimal resolution of the associative operad. And now you can look at associative algebras in an orthogonal way. You can see them as yeah, you can see them as algebras over the associative operad, but you can also see them as operads concentrated in arity 1. So if you have an operad where all the pn's are 0 for n then greater than or equal to 2, then if you look at the axioms, you will get only trees. You will get only trees with one input and one output, and the axioms will be just saying that this composition is associative. So so you actually just operads concentrated in arity 1. This is just associative algebras. So now you have an arrow here going from associative algebras to operads. And then you can wonder, well, oh, but is this square that I've drawn extensible? Is it possible to extend it to another square starting at operads? And the answer is yes. There is an operad O, and when you take algebras over O, you get operads. That's a bit odd for the mind at the beginning. So there's a operad that encodes operads, and there is also a minimal resolution of it, O infinity, in which A infinity embeds. And when you take algebras over O infinity, well, what you get is operads up to homotopy. Up to homotopy. What do I mean by that is an operad where the parallel and sequential axioms are relaxed up to homotopy. So you remember parallel and sequential axioms. These were, you could see them as these drawings. You remember equal. But then what I'm going to do is, exactly as in the case of associative algebras up to homotopy, I'm going to replace this equality sign by merely, by an equivalence by an homotopy, a specific homotopy between these two. So I should draw the parentheses. And the same for the parallel axiom. And I will get this way an infinite tower of homotopies encoding this associativity, this up to homotopy associativity. And so you can complete the square, of course, here. And now you can wonder. So I had polytopes. Yeah, maybe I should just copy it on the next slide, and then say, well, here for infinity, this was isomorphic to the cellular chains on the family of polytopes, associahedra. And then you can wonder, well, is there something equivalent for O infinity? Is this cellular chains on some family of polytopes that generalize the associahedra? And the answer is yes. These are called, well, I call them operahedra because, yeah, you see, you had associative algebras, then you have operads, and then associahedra, operahedra. And great. And then my question was, well, can we follow the same thread of thought to define the tensor product of two operads up to homotopy? So we had a tensor product here, and can we define a tensor product here? And this is what I've done in this article in my thesis. So I defined first the Lode realizations of the operahedra. So you see that they generalize the associahedra. You of course you get the associahedra But you also get another important family of polytope, which are called Permuta Idra. And these are the faces of Permuta Idra are in bijection with ordered permutation, ordered partitions of 1n. What is it? Yeah, and these. So how do you find these polytopes? Well, you start from a planar tree, and you associate to it a polytope. And I think yeah. And the faces of the polytope are in bijection with nestings of the tree, but this is, I could also say, parenthesizations of the tree. So to get the associahedra, you just look at exactly the same drawings that I've been doing two times now. So you look at these planar trees here with well, actually, I think you would need you would need 5 vertices, and then you look at all the ways of parenthesizing this tree. And when you get a full parenthesization, this will give you a vertex in the polytope. And you obtain the permutohedron by looking at these kind of trees, like the corolla-like trees. And you look at parenthesizations of these trees, and these give you vertices in the permutohedron. And to go on higher dimensional faces, you just forget nests. So if you have another nesting here, I will not draw the leaves for convenience, but if you have this other nesting here, well, so the edge between the two, it will be indexed by the same tree with all the same nestings except the ones that are not common. You can only keep the common nest. So you keep this one and this one. And yeah, so the top dimensional cell, it will be just, well, no nesting, or just a trivial nesting, like, altogether. And these are really homotopies. You know, you should think of them as the points are real parenthesizations, and then edges are homotopies between these parenthesizations, and two faces are homotopies between homotopies, and so on. Yeah, perfect.
Can I ask what way does the fact that the tree is planar, what role does that play here?
Okay, so it plays the role that I didn't mention is the fact that what I'm considering here is non-symmetric operads. So in my, if I wanted to be more precise, I would write here non-symmetric operads, and then O is encoded by, you would get planar trees here. But if you want to encode symmetric operads, then you need non-planar trees. And you need not to color by, yeah, you need a colored operad, and you don't only need to color by the natural numbers, but you need to color by groupoids. But this was developed by Ben in one of his paper, that this requirements. Is it clear why I'm using
in particular yeah, that's fine. I mean, the notion of nest doesn't really see planarity, right? Like you could nest two edges that are not sort of planarly adjacent. Yeah, thank you.
Yeah, but I guess to define the actual polytopes, so I have a way of getting coordinates out of a parenthesization, and to actually define the polytope. And for this, I need an ordering of the edges. But yeah, you're right. You can define an ordering on the edges on non-planar trees. So so I guess actually this can be this should not be so difficult to generalize to. I don't think it. I think it's probably straightforward. Yeah, didn't think about this. Yeah, but I restricted myself to non-symmetric operads. Yeah, well, yeah, maybe something I should say. I don't know if some people here are close to combinatorics or algebraic combinatorics, but these polytopes are graph associahedra. They are particular cases of graph associahedra as defined by Carr and de Vados. They're also generalized Permuta Idra as defined by Postnikov. And yeah, they extend some realizations of Vincent Pilot. He called them sign tree associahedra. Yeah, so the second thing, once I have these polytopes, what I do with them is I define an approximation of the diagonal and a compatible operad structure on them. So I'm following exactly the same thread of thought as before. And to do this, well, we need a good orientation vector for each polytope. And it turns out that these vectors, it's not every vector that defines an approximation of the diagonal. There's only some vectors. And it turns out that these vectors, they live in the chambers of a certain hyperplane arrangement. So here you have, so this is the braid arrangement on the left. Yeah, maybe I should already so this is the braid arrangement on the left. And on the right, you have I call this, this is not the right name. In the paper, sorry, it's the fundamental hyperplane arrangement. And here you see the fundamental hyperplane arrangement for the three-dimensional permutohedron. And you see that I should write it carefully. Permutohedron and it actually it refines the braid arrangement. So it's and it turns out that these hyperplane arrangements, well, they're present in the literature, but they were not really studied for themselves. And so when you want to handle the polytopes with the topological operad structure, it turns out that in this case, there's more degrees of freedom than in the case of associahedra. And you have to make a coherent choice of chambers in the hyperplane arrangements associated to each polytope in order to get an operad structure. And well, one of the first theorems of my paper is that there's actually there exists such a choice. And in fact, there are many choices. I exhibited a second one, and I imagine that there are a few of them. And I think, this is a question I didn't really investigate, but there are other choices. So you have some degrees of freedom here. And finally, I've been able to describe the image of this diagonal approximation. And this gave me an explicit formula for the tensor product of operads up to homotopy. And so let me finish on this by explaining to you a little bit, showing you the formula and trying to explain it to you a little bit. So it's a very combinatorial, down-to-earth formula. And so you need for it these xn, which are the pairs of subsets of 1n, which have the same cardinality, zero intersection, and whose minimum is in I, and I should say non-empty, non-empty subsets. And here it is. Here's the formula. So it says that a pair of faces. So remember that you have on the polytope. Well, a polytope, it's associated to a certain planar tree, and faces are in bijection with nestings. So if you have two faces, well, you have equivalently two nestings, n and curly n and curly n prime. And what I'm saying is that well, you'll have a pair of face would be in the image if and only if there exists a nest in N which has like the cardinality of the intersection with I is strictly bigger than the cardinality of the intersection with J, and or there's a n prime in curly n prime, so another a nest on the in F in G that verifies the opposite condition. And let me just draw a small example. So if you have, let's say you have these two faces. So here we're gonna order the edges of the tree 1, 2, 3, 1, 2, 3, and then this will be in the diagonal. So we need to write the pairs ij. Since we are in R3, there's only three such pairs of subsets. And then what you have to verify is that well, there's n, so this will be F, this will be J, and you have, well, no, this color is not good. You have an n here, you have an n prime, and so what you need is you look for every pair. So if you look at this first one, 1, 2, well, you need either a nest on the left that has bigger intersection with 1, that contains 1, but not 2, or you need a pair, you need a nest on the right which contains 2 but not 1. And here, unfortunately, it's not the case. So these two, this pair is not in the diagonal. But you could do the same for. Let's try to find something that works. Maybe this one and this one. So you get something on the right that contains 2 but not 1, and then yeah, and the nest on the left contains 1 but not 3 and 2 but not 3. So this pair will actually be in the diagonal. Yeah, finally, so this formula is computer friendly. I worked with Hugh Thomas this summer, and he designed very quickly a computer program that was calculating these pairs up to dimension 8. It actually comes from a universal formula which is obtained geometrically by playing with the fundamental hyperplane arrangement of the polytope. And this formula can really be applied to new cases of interest. It actually applies mutatis mutandis to any generalized Permuta-Idra. So one of them are, well, part of them are the multipliedra, which encode morphisms of infinity algebras, or all the polytopes that encode modular operads up to homotopy that are in Ben's paper, or a few other algebraic structures of interest in different fields of mathematics. And I think this is all I've got to say. Thank you very much.
Okay, yeah, thank you very much. And we have time for some questions.
Yeah, would be very happy to answer. I guess this was a bit quick.
So I was wondering, in what way did the formulas simplify if you're tensoring together, say, or just in the A infinity case,
Yeah.
An associative algebra with an A infinity algebra, or an AN algebra with an AM algebra? Is there anything concrete?
That's a good question. So already for if you want to just treat the case of A infinity algebras, you can restrict yourself to the conditions for which A and I and J have cardinality 1. And so you can forget about all the higher conditions on like all the for higher cardinalities, you can forget them and have only test only these ones. I didn't look into and when you have these smaller cases. I think this would be interesting. It's sure that it admits simplification. Yeah. Is there? Okay.